first aspect that we are going to discuss in the reconstruction filter is a low pass filter. A low pass filter is basically working on a specific frequency which are retained from 0 to any cutoff frequency referred to generally as FC. This FC in this particular graph has been chosen to be A. The amplitude of a low pass filter under normal cases is 1 in the time domain. With this base, let us go on to see what is this cutoff frequency. It tells us that if there is a speech signal which is having various frequency components like 50 Hz, 75 Hz, 60 Hz, 200 Hz, 500 Hz, suppose we want to have a band of frequencies between 0 to 75 Hz, either for a speaker recognition system or to implement a specific system which would identify a particular voice where you know that this voice has generally the low frequency. Under such a case, we would preferably go for a low pass filter. The basics as mentioned is the cutoff frequency is the most important part in the design of a low pass filter, as the amplitude of the low pass filter is generally constant. It is 1. If higher amplitudes are required, we have to amplify the low pass filter by applying a constant or multiplying the low pass filter with a constant. So this is as far as the time domain response is concerned. Most of you would also recall that this is called as the ideal low pass filter response. It is also called as the brick wall response because just see, the response looks like a brick wall, and it is not possible for any low pass filter to get a frequency like this, though ideally this is what is shown because this is what gives us the sync function also. Normally the low pass filter has got a response which is going to have, at after some stage it will taper down and then it will become 0, and usually it will try to touch 0. It will not touch 0. There will be a small gap between 0 and that line. Maybe when we consider signal processing, we will go more in depth about the structure of the low pass filter. For now, we can consider that this brick wall response is an ideal response which is not physically realizable, or it cannot be practically implemented in most of the cases. So the response of such a brick wall response, again that is also a derivation in signal processing, is going to be a sync function, and that is the solution that has been given. The reconstructed signal h of n would be given by 2fc into sin n omega c divided by n omega c when n is not equal to 0 and when n equal to 0, because when n equal to 0 this term becomes 0, so the entire expression tends to go to 0. Hence this is not possible to be implemented at n equal to 0. So when n is equal to 0, we go on to apply the Taylor series, which tells us that make tend n to go to 0, and as a result our solution at n equal to 0 would be 2fc. In most of these cases, it is a band limited signal that is generally discussed, and as a result the cutoff frequency chosen is usually fs by 2. Only under such a case it is seen that the sync function is realized. This is another drawback or another limitation which prevents the use of a low pass filter in image processing application. Exactly a low pass filter, a small variation or a variant of a low pass filter is what is generally used for applications. As has been mentioned here, there are two issues when we are applying the NYQUIST theorem. One is when the signals are not band limited, we are using a band limiting filter which is applied, which has a cutoff frequency as given before, half of the sampling frequency, and this is called as a pre-filter. You would recall that most of the sampling process has got a pre-filter and generally a post-filter. And generally, the problem with a low-pass filter is that it is an infinite filter, and as such, it is not realizable. So, better we would like to go to finite length filters, shorter finite length filters used in practice for both pre-filter and interpolation filter. We will see what it is when we consider the FIR filter design in detail, and maybe we will have a small discussion on this particular aspect alone. Now we will just see the expression of this. The reason being, when we say that it is a finite length filter, maybe some of you would recall that FIR filter is a finite length filter, and it has a response which could be having a tap of 3, a tap of 5, which is a finite value, unlike other cases of filters where usually n tends to infinity. That is what has been mentioned here. Preferably, we would like to go for a FIR-based pre-filter, a low-pass filter, or even here, interpolation filter is generally implemented using the FIR concept only. That is because if we go in for IAR or any other method, the filter tends to go to infinity, and as a result, it may not be easily realizable. And the basic problem of this interpolation is, you would recall, interpolation is basically upsampling. Usually I would prefer to discuss these two slides even at the end of signal processing, that is up to the filters. Now just we will have an idea about what it is. So interpolation is basically adding zeros to a signal or to an image, whereby we are increasing the size of the image. We have seen the linear interpolation. You have some idea. That is, a 2x2 image was converted into a 4x4 image. That is interpolation in 2D. Similarly, interpolation is also obtained in 1D. And during this, again, even after the interpolation, we generally see that there would be extra spectra. That means we have something called as additional images, or they are called as duplicated images, aliased images. Different terms are used for explaining that spectrum that results after the interpolation process. They also need to be removed, and for that a specific interpolation filter, which is almost like a sinc function, is being used. And we could see here that only on the use of such a filter, the resultant reconstructed image would be got. And usually the structure is, you could see in our previous reconstruction filter, it was 2FC. Here we have used Fs into M into N, and though there are two signed components, we have not got those two components specifically. It is just in order to counter for the cutoff frequency, which is the sampling frequency. This Fs of M of N is written, which is the sample frequency, and you could see that there is a sinc function corresponding to the x coordinate and another sinc function which is corresponding to the y coordinate. With this base, we have gone in for considering a basic interpolation filter, which could be applied for images, but more in detail may be considered after. Only these two slides would be preferable to be discussed after the discussion of filters in signal processing. So completes our discussion on basics of sampling. Now we would like to move on to convolution, and when we move on to convolution, the first thing that comes to our mind is, what is this convolution and what is the need of convolution? Because various types of convolution actually exist in signal processing as well as in image processing. The convolution that is of interest to us is the basic linear convolution, which we call it as the discrete convolution or the continuous convolution in signal analysis, and here it is just going to be called convolution. So let us quickly just recall what is the discrete time convolution, how it is obtained, and what is basically done in a discrete time convolution. How many elements are there? Will there be a similarity in 2D convolution? This is what we need to consider and analyze. That is why the discrete convolution has been discussed in detail, preferably with an example. For people who are familiar with discrete convolution, maybe this would look to be a repetition, but a discussion of this would be important for the analysis of 2D convolution. The discrete convolution, without going too much into the theory behind it, is generally got when we have a system whose input is x of k and which has another input, which would be an impulse input, resulting in an impulse response. Then the output of such a system is generally given by the convolution of the input and the impulse response of the system. Usually it is represented by y of n is going to be equal to of n convolution h of n. The mathematics behind this is k is equal to minus infinity to plus infinity x of k into h of n minus k. This is the expression that is generally used for convolution. This expression will be also extended to the 2D case. So what happens when we have an example like 5, 1, minus 2, 4, and 1, 2, and 3. When we have a value like this, we have that k is equal to 5, 1. At k equal to 0, 1, 2, and 3, the values of x of k are 5, 1, minus 2, and 4. And basically what is generally seen is that for each value of k, or for each value of n, we need to substitute and find out what would be the resultant. So if we quickly go on to what is usually done is, this is replaced with a dummy variable called as x of k, and this would be h of n minus k, as has been seen in the previous slide. So when n is equal to 0, this results in x of k convolution h of minus k. So when k is equal to 0, 1, 2, and 3, which are the values of x of k are, that is the magnitude or the amplitude of the signal, is 5, 1, minus 2, and 4, as has been written near each of its values. Next, what we do is, similar to that, we would like to represent, first we are representing the signal x of k, next we would like to represent h of minus k directly. Being the first case, h of k has been represented, then we are trying to represent h of minus k. So h of k would be, it is only 1, 2, 3, zeros after that value we are just going to ignore. So at k equal to 0 it is 1, at k equal to 1 it is 2, and at k equal to 2 it is 3. When we say it is time reversal, or what you call flipping about the time axis, what happens is that what is available at 0 is retained, and the other two values are shifted to the negative time axis, resulting in at k equal to 0 it becomes 1, at k equal to minus 1 it becomes 2, and at k equal to 3 it becomes minus 2. So what happens is that we have got now x of k and h of minus k, both are available. This is available in red and this is available in black. So let us try to write both of them as such and multiply each of the terms, and if there is a summation required, we will just sum up the elements. In this particular case, there is no summation because k is available only at k equal to 0. We have both h of minus k and x of k. At k equal to minus 1 or at minus 2, only h of k is present. Similarly, at k equal to 1, 2, and 3 also, only x of k is present, which means the resultant here would be 0. Hence, we would get 5 into 1 is 5, resulting in y of 0 is going to be equal to 5. So the usual process is that first represent x of k, then represent h of k, and finally we would like to represent. Let us go on to the next case, which is going to be n equal to 1, whereby what we are going to redo is, when n equal to 1, we are trying to find y of n, x of k remains same. Here it is h, n minus k, 1 minus k. So let us try to see what happens here. As usual, please note, in all the cases, representation of x of k remains the same, only flipping or what you call shifting of the signal is applicable only for one of the signals, and usually the general concept considered is that whichever is the simpler signal, that is being flipped. So here, since this is a shorter signal also, that is why h of k is preferred to be flipped. So once we have got this, we have got 5, 1, minus 2, 4, which is the same as x of k. After that, we try to represent h of k, and h of k is going to be equal to, h of minus k is there. Next, we try to get h of minus k minus 1, whereby it will be shifted towards the right by 1 position. So we will be having it as 1, 2, and 3, which is either h of minus 1, h of 1 minus k, or it will be h of minus of k minus 1, because you would see when you consider this, this becomes 1 and this becomes 1 minus k. So what happens? What happens is that we rewrite x of k 5, 1, minus 2, and 4, and we also rewrite at n equal to 0 it is 2, and at n equal to 1 it is 1. We rewrite those values and multiply them as before. 5 into 2 gives us 10, 1 into 1 gives us 1. So the summation of this, which was not there in the previous problem, is now carried out. So it is 10 plus 1, which gives us 11. Considering this, we would repeat it for various values, giving us the resultant as 15 in this particular case and 3 in the next case. Because we're going to shift this by 2 positions, so it is 3, 2 and 1 here. So when we multiply, this is 3, this is minus 4 and this is plus 4. And when n equal to 4, we would like to get the resultant as h of k minus k, which means we are getting the resultant as 3, 2 and 1, giving us the answer minus 6 and 8, summation of which results in 2. We would also like to get a value for n equal to 5, and thereby the answer is 12. We repeat it for n equal to 6, we see that there is no overlap between x of k and h of k, hence our resultant is 0. Since our resultant is 0, we would see that there is no point in proceeding further, which means no use trying to again proceed and find out what could be the convolution at n equal to 7 or at n equal to 8, as the resultant convolution at these points are definitely going to be equal to 0. So we have got a limiting case which says that from 6 onwards, the value of the convolution is 0, so we can ignore it. Similarly, let us also try to find out the negative half, because we have started from 0, n equal to 0. What happens at n equal to minus 1? So at n equal to minus 1, a similar expression is seen, and what is generally seen is that we would see it is obtained as, here we have got x of k, here we have got at n equal to minus 1, this is what is at n equal to 1, it was 1, 2 and 3. We have shifted it by 1 bit towards the left because it is minus shift, or what we call minus 1 minus k. So that's why we see that again there is no overlap. So the resultant is 0, which tells us that at values beyond n equal to minus 1 and from n equal to minus 1 onwards, the resultant of the convolution is going to be 0. So we have come to a solution whereby we could say that less than 0, that means from n minus 1, minus 2, etc., y of n is 0. At n greater than or equal to 6 also y of n is 0, and the value of n between 0 and 5 is as is shown in this particular case. So the concept of discrete convolution is basically consider one signal, consider the other signal, shift whichever is the shorter signal, or having a simpler structure. Once we have flipped it, then keep on shifting it and multiplying it with the first signal, multiply and add to get the solution. This is basically the concept of discrete convolution. With this phase, maybe we could start off with the next convolution, which is important in image processing, namely the 2D convolution.